So back to the pizza. Here's our recipe again. We've got 4 crusts, 10 cups of cheese, and 15 ounces of sauce. How many pizzas can we make? Yeah, think about that for a minute, huh? I heard 1, I heard 2. 3. We can make 3 pizzas. How do we know? Well, what you kind of have to do, and you can do these in your head, is you look, well, 4 crusts, how many pizzas could I make? 4. 10 cups of cheese, how many pizzas could I make? 5. 15 ounces of sauce, how many pizzas? 3. So we understand, because we've at the very least seen pizza being made, you make the pizzas, you use up all the sauce on the 3rd pizza, you can't make more because there's no more sauce. It stops, right? What happens to those the extra crust and the extra cheese? They sit there on the counter, right? Maybe you make garlic bread or something, but you can't make pizza out of them. You don't have any more sauce. Okay, this happens in chemical reactions as well. We don't always have just the right amount. In cooking, it's extremely rare to have exactly the right amount of everything, right? Usually, there's one thing that's going to limit how much you can make. You're going to run out of that, and then it stops. So let's just look at what we did in our heads to figure this out. So 4 crusts. We're thinking, well, I can make 1 pizza for every crust. Right? So I can get 4 pizzas out of that. I'm going to call them P. 10 cups of cheese. We did this one already. 1 pizza per 2 cups of cheese. So that is 5 pizzas. And then the sauce, 15 ounces of sauce. And for 1 pizza, we need 5 ounces. Why do we need 5 ounces of sauce? Because the recipe says so. It wasn't meant to be a trick question. 3 pizzas. We look at this and we understand that 3 is the most we can make. 3 is the smallest of these numbers. So we're going to follow this same pattern with chemicals. You take each of your reactants and you figure out how much of the product can you make. The answer is going to be the smallest number. You're not going to add them all together. You're not going to pick the biggest one. You just pick the smallest number, and that's the answer. The sauce here is called a limiting reactant or a limiting ingredient because this is what's limiting how many pizzas you can make. Okay, so here it is in pictures. So we got enough crust for 4 pizzas, enough cheese for 5, but only enough sauce for 3 pizzas. It limits the production. So we call the tomato sauce the limiting reactant, or sometimes the limiting reagent. The maximum number of pizzas is called the theoretical yield. Because in theory, if everything goes perfectly, that's how many pizzas you could make, right? So we take our ingredients, we calculate how much product we can make. The smallest amount of product is the theoretical yield. The reactant that gave us the smallest amount is the limiting reactant. Make sense? So, same concept, chemical reaction. Just like baking, cooking in the kitchen, in a chemical reaction, it's very likely that one of the reactants is going to get used up and that there's extras of the rest. Once that reactant gets used up, no more products are made. Just like with the pizza. Once you're done with the sauce, you can't make more pizzas. So the reactant that limits the amount of product is called the limiting reactant, and that limiting reactant gets completely consumed. The reactants that are not completely consumed are called excess reactants. So those are the ones you have extra of. So we talked about theoretical yield. Then there's the actual yield, right? This is the amount that actually gets made, because sometimes stuff happens, right? Perhaps when we're making the pizzas, we got distracted by a YouTube video and didn't get to back to the oven, and we burned one. And we really burned it. So can we count that as a pizza that we've made? Not really. We're not going to be able to serve it to anybody. Or we drop one on the floor, right? We have dogs, and so you drop a pizza on the floor, you're not going to eat that because it's going to be covered in white dog hair. Ugh.
I still feed it to my brother.
You feed it to your brother? Yeah, that could happen. So the actual yield is how much actually gets produced, because things can happen. And things can happen in a chemical reaction as well. Not like burning pizzas, but there are various factors that can cause the reaction to not produce as much as theory says it should. So that's the actual yield. We're interested in the relationship between the actual yield and the theoretical yield, and so we use percentages to describe that. The percent yield expresses the efficiency of the reaction. So, if you're going to get a job at me and Ed's making pizzas, and your percent yield is only 50%, because you keep dropping pizzas on the floor, you're not going to stay around very long, are you? Now, are they going to fire you for dropping one pizza in a week? Maybe you had a 98% yield. No, probably not, because, accidents happen. But that percentage gives us an idea, how well is this working out? So the percent yield follows that same pattern of part over whole times 100. Here the part is the amount we actually make, divided by the whole thing, how much in theory we could have made, times 100 to make it a percentage. So this is a summary slide. The limiting reactant is the one that gets used up. It's the one that gives us the smallest amount of product. Excess reactant is everything but the limiting reactant. Theoretical yield is the amount calculated based on the amount of limiting reactant. Actual yield is how much you actually make. Now this number in a word problem on an exam would have to be given to you. In an experiment, that's the mass that you actually end up with, and you would calculate the theoretical yield. And then there's the equation again for percent yield. So let's apply this to chemistry. Going back to our combustion of methane problem. So 1 molecule of methane reacts with 2 molecules of oxygen to produce CO2 and water. What this tells us is that every 1 molecule of this reacts with 2 of those. What if there were, let me see what the next slide says. What if we had 5 molecules of methane and 8 molecules of oxygen? So we can do this thinking of a picture, or we can do the math. So let's do the math. So 5 molecules of methane. We get 1 molecule of CO2 for each molecule of methane. If we had enough oxygen, this would react to form 5 molecules of CO2. You okay with that? Then we're going to take the oxygen and do the same sort of calculation. We're told that we have 8 molecules. We get 1 molecule of CO2 from every 2 molecules of oxygen. So we do the math there, and that tells us we can get 4 molecules of CO2. And if you look at this, you can count up the number of red balls over there and over here and see that that's true. So this gave us 4 molecules. This one gave us 5. Which is smaller, 4 or 5? 4. That's a number we can handle at 9 a.m. A question. I can't ask the question, but, I can mumble through. So we're going to get 4 molecules of CO2 as our theoretical product. Does that make sense? What's the excess reactant then? Well, this was the limiting reactant. The one that could make more, this is excess. Because what's going to happen is one of these is just going to be left hanging out. Like the pizza crust that we didn't have any sauce to put on. Right? It's just still there. So that's all nice with molecules and stuff, but we're going to do this with grams. And so we're going to have moles in the middle again. Grams to moles to moles. So this is how your book presents it. And this is fine. This is not how I like to think about it, but if you like this way, you go right ahead. You take each of your reactants and you convert to moles and then to moles of the product. The book says, well, stop there and find out which one's smaller. Pick the smaller one and then continue and convert to the mass. So what I like to do, because I think it's not much more work and it's less thinking. So less thinking is always good. I'm going to say, well, let's just go all the way to moles of product. And then look for the smaller. So what I'm going to show you, demonstrate in lecture, is when we have a limiting reactant problem, we have two reactants, a mass of each, and we want to know how much product is actually, or is theoretically can be made. We're going to take the mass of one reactant, go to moles to grams, and then we're going to take the mass of the other one and do the same type of calculation. So we're going to end up with two masses, and we're going to just pick the smaller one.
You need to write grams.
I did, thank you. Yeah, because we already had moles. So that's, yeah. I was doing that to see if you're paying attention. Okay, that better? So here's an example. Ammonia can be synthesized by this reaction. What's the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? So there's my balanced chemical equation. You need to have that because we need to know how many moles of hydrogen and how many moles of nitrogen make how many moles of ammonia. I'm going to take my numbers and stick them under the appropriate formulas. So hydrogen is 5.22 kilograms. And nitrogen is 31.5 kilograms. And the question, what yield of ammonia is NH3, you're supposed to know that one, in kilograms? So this problem is different than previous examples because we have two numbers. So we're given information about both of the reactants. We're going to have to do two calculations. Grams to moles to moles to grams. So again, we've got the kilogram thing going on here. So I'm going to show you a different way to deal with that. You can do the same way we did before, but I'm going to show you a different one here as well. So grams to moles to grams. I'm going to do one for the hydrogen and one for the nitrogen. So I'm going to start here with 5.22 kilograms of hydrogen. And I put the kilo in red because I just want to ignore it for a while. So we're going to go grams to moles to grams. So moles of hydrogen to moles of what? The one with the question mark. NH3. So we don't want to find out how many moles of nitrogen. This is our question. We want to find out how many moles of ammonia. And then grams. So we stick our units in here. And what I'm going to do here is I'm going to put grams of H2 down here just like normal. I'm going to cancel the gram part and not the kilo. The kilo means 10 to the 3, and it can just sit there by itself. It's okay. So I'm canceling grams of hydrogen and moles of hydrogen and moles of ammonia, and I'm left with this leftover kilo and grams of ammonia. So moles in the middle, 2 moles of ammonia from 3 moles of hydrogen. We need the molar mass of H2, so that's 2 times 1.008, or 2.016. And then we need the moles of ammonia. We should probably go ahead and calculate that, because I mostly remember it, but then I usually screw it up. It's 17 something.
17.03.
Thank you. So 17.0, it's actually 034. 031. See, now that's going to bother me because I somehow think there's supposed to be a 4 in there. I get, with 1.008, I get 17.034. Okay, so we can calculate that. 5.22 divided by 2.016 times 2 divided by 3 times 17.034. And I get 29.403 grams of ammonia. And then what else is left here? I didn't cancel this kilo out, right? It's still there, so I should write it in there. Yeah, I just did 5.22. Because what actually is happening here, when we convert from kilograms to grams, and then later convert from grams to kilograms, those two conversion factors cancel each other out, right? So I can make it shorter doing this. Now, that might be confusing to you. So if that's confusing, don't do it. So this next one I'll do like I did. You like how I did the first one with the kilograms? Did that make sense? Okay. So let's do our second calculation that way. So we've got, so I did the hydrogen. Now I'm going to do a very similar calculation for the nitrogen. So I'm going to start with the mass of nitrogen. So I've got 31.5 kilograms of nitrogen. But the kilo means 10 to the third, right? So what we did in that first example is we say, well, instead of writing kilo, I'm going to write what it means times 10 to the third. And everybody seemed to be pretty much okay with that. So grams of nitrogen to moles of nitrogen. To moles of what? When we were calculating pizzas, how many pizzas we could make, what did we calculate for each of the ingredients? The number of pizzas, right? We're going to calculate this mass again. Now we're just starting with the nitrogen. So here you're always going to end up with moles, grams of the thing with the question mark. Sometimes people go off and do lots of other stuff that's really nice, but it doesn't answer the question. So we want moles of ammonia. And I'm going to have grams of ammonia. So we're going to get our units all fixed up here. So in the middle here with the moles, we have 1 mole of nitrogen gives us 2 moles of ammonia. So 1 mole of N2, 2 moles of HN3. I'm sorry, NH3. This last term should look a little familiar. Grams of ammonia to moles of ammonia. That's exactly the same as this term. That's not a coincidence. We already have the molar mass because we had to calculate it for the first one, so we'll just stick it in there. And then here, moles of nitrogen and grams of nitrogen, that's 2 times 14.01, 28.02. So I've got 31.5 EE3 divided by 28.02 times 2 times 17.034. And I'm ending up with this really big number. What else do I need to do? I need to convert back to kilograms. So I'm going to put 10 to the third grams in the denominator, kilograms on top. I've got the prefix on one side, I've got the 10 to the something on the other side. Don't put them together. They need to be on opposite sides. So this is going to be what, 38.3 grams? I'm sorry, kilograms. Any questions? Have I finished the problem yet? Nope. Super close, did all the hard work. I have 2 answers, I need to choose one. How do I pick?
Smallest.
Pick the smallest one. So this one is smallest, right? So the theoretical yield is 29.4 kilograms. And I often call theoretical yield tie. You need to identify which of those 2 answers is your answer. What's the limiting reactant in this problem? Hydrogen. So we find the smallest one, and to find the limiting reactant, just look back and see which reactant gave you that smallest number. It was hydrogen. Any questions? Yeah.
Can we do the conversion, like the one on top, where you cancel out the grams and
Mm-hmm.
with other conversions?
Yeah, you can, some people feel like it's like hand waving or voodoo or magic or something. There's a lot of little things that you do at either end sometimes. Like if you had milligrams, and then they want kilograms. If it's the same unit on each side, if it was nanograms here and you wanted nanograms, you can write it out and prove to yourself how the conversions cancel each other out. Yeah. And if that doesn't make sense to you, write the whole thing out. That's entirely valid. Okay? This isn't about speed, right? It's about getting to the correct answer. Any other questions? Okay. Gotta do this one. Then we'll stop. Mining companies use this reaction to obtain iron from iron ore. The reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams of iron, determining the limiting reactant, the theoretical yield, and the percent yield. Okay. Take the numbers, write them under the equation. So 167 grams of Fe2O3 and 85.8 grams of CO and 72.3 grams of iron. Oh, I didn't need this CO because it's up there. Just thought that looked weird. Okay, well that's different. Determine the limiting reactant. How do we determine the limiting reactant? We have to calculate the theoretical yield, right? We have to see which one gives us a smaller amount of product. Well, they also want the theoretical yield, and they want the percent yield. If we calculate the theoretical yield, that will give us the limiting reactant. Here we've got two products. Which one are we interested in? The iron. This sentence told us, mining companies use this reaction to obtain iron from iron ore. This is the thing of interest. Is this the theoretical yield? That's the actual yield. Because this is saying this amount of that and this amount of that produces this. You have to be given the actual yield. So this is the actual yield. So let's maybe move it over here and call him I. Actual yield is 72.3 grams of iron. And then I'm going to take that away because what am I trying to find for the theoretical yield? Grams of iron, right? So this is my question mark. I'm trying to calculate that to get the theoretical yield. You with me? Calculating a theoretical yield, I have to do two equations if I have two reactants with masses, right? So thankfully, these are just grams. So I'm going to run through these fairly quickly. 167 grams of Fe2O3. So grams of that to moles of that. Grams to moles, moles of what? Iron, the thing with the question mark under it. To moles of iron to grams of iron. Okay, fill in the rest of the units to cancel out. So the one in the middle is the easy one. Mole to mole ratio. 1 mole of iron gives us, 1 mole of Fe2O3 gives us 2 moles of iron. This last one's pretty easy because it's just the molar mass of iron, 55.85. And then we need the molar mass of the Fe2O3. So I've got 2 times 55.85 plus 3 times 16, 159.7. I didn't write it on the screen because I'm not going to have enough room. Okay, so we can do that calculation, 167 divided by 159.7 times 2 times 55.85. Problems using 3 significant figures. I'm going to write down 2 extras. Okay, so there's one answer, or one potential answer. Excuse me. I need to do the same thing with the carbon monoxide. So 85.8 grams of carbon monoxide. Grams to moles to moles to grams. Moles of CO to moles of, again, the question, moles of iron. These are both, we're starting in different places, but we're ending up in the same place. So I put my units in there. Forgot what I was doing. So mole ratio, 3 moles of CO gives us 2 moles of iron. 2 moles of iron, 3 moles of CO. The last one's also easy because we already did it. And then carbon monoxide is just carbon, 12.01, plus 16 for the oxygen, 28.01. Wrong place. 1 mole to 28 grams. And this is giving me 114.05 grams of iron. What's my theoretical yield?
114.
Yep, this is my theoretical yield right here. Theoretical yield equals 114 grams. What's my limiting reactant? Carbon monoxide. This is the smallest. Just go back and see which one. So it's this guy right here. So limiting reactant is carbon monoxide. You have to specify that in a question like this. You can't just assume that I'm going to look at it and know what you mean. And then the percent yield. So percent yield is actual over theoretical times 100, right? So we were given the actual yield, 72.3 grams. Our theoretical yield is 114, and I'm going to carry those extra digits to avoid rounding errors. So I've got 72.3 divided by 114.05 times 100, and I'm getting 63, look, this should have 3 sig figs, 63.393%, 63.4% is our percent yield. Any questions?